Thank you, Nuno. Thank you all for being here. So because we're going to start a little bit late, perhaps I won't have the time to do the last part of the talk, but that's a sketch of the proof. So usually by this time, people don't get much of the talk anyhow. So you shouldn't, you won't miss much for, or it's quite likely that this is a part that would not have been the most interesting to most people anyhow. Okay, so let me first start by quickly saying what this work is about. So here's a very simple physical situation. You have a pendulum suspended from the ceiling, and you're trying to stabilize it at any angle. And you have to decide where are you going to hold. So we have a weight here, a mass, attached to the ceiling with a rod. Where are you going to hold this? Where are you going to put your finger on the rod if you want to make your job at stabilizing this mass the easiest? Quite intuitively, so here are different positions, which I call B1, B2, B3. Quite intuitively, you will put it at the very bottom. So that's the optimal actuator placement. That's what I'm going to call the optimal actuator placement. So the subject of this talk is to try to make this more formal and try to understand the mathematics behind such problem. So how to place the actuator to make optimal control more efficient, or similarly, or dually, how to place a sensor to make estimation more efficient. So this simple problem here is very simplistic. What are these type of results applied to in general? Well, any kind of sensor placement problem. Here, sensor placed on the shoe. Here, sensor placed on the human body, or here, in some very large scale sensing operation. And there is an abundant literature on optimal actuator and sensor placement. So I'm not going to say much about this. What we're going to do here is that in some situation we can obtain an exact situation, an exact answer, the exact location of the optimal actuators or sensors. Okay, so let me immediately start with the problem formulation. As you can see, sketch of proof. So perhaps I will skip that. So we have a finite dimensional linear system. X dot is AX plus BU. I'm going to call B here the actuator of the system. We set up an LQ control. So we're trying to find a control that will minimize this cost functional. Here, X0 is the initial condition of the system. The question is, how to choose the actuator, B, that will minimize J. So here J will depend on B through some kind of, in some complicated way. How do we find the optimal B to minimize J? Okay. Now, of course, you can say I'm not going to design a controller, an actuator B, for a given initial condition. So you might want to try to find a B that will optimize J for X0 distributed randomly. So we're also going to do that. Okay, so that's the next question, how to choose the actuator B that will minimize the expected value of J, expected over the potential possible initial condition. Okay, in the estimation setting, this is what we have. We have a linear system driven by noise. Here I did not try to control. You can add a control, does not change anything. Observe here through this linear equation. That's a typical setting for a continuous time Kalman filter. W and V are independent Wiener processes. I'm going to call C the sensing matrix of the system. Now here K is the covariance of the estimation error. So what we want to do is choose the vector C, the sensing matrix C, that's going to minimize the covariance error. So we have a sensor here. Where do we place it if we want to have the best possible estimation? So that's the optimal estimation problem. So I'm going to switch back and forth between actuator and sensor because we'll see that problems are the same. But I'm mostly going to use the terminology of optimal estimation. But you can replace estimation by actuation, sensor by actuator at any point in this talk. Okay, so that's what we want to do. That's a problem statement. Okay, so why are these problems the same? And basically, both of them boil down to studying somehow the Riccati equation. So J of X0, the optimal LQ cost you could achieve, is given by this, where K here is a solution of this Riccati equation. Okay. So this is a known fact from linear system theory. So now we can rephrase our original problem, the optimal actuator design problem, as minimizing the trace of LK. Take, for example, here L to be X0 transpose, X0, X0 transpose. So this would exactly be LK, where K obeys the Riccati equation. If you take L to be the identity, you'll obtain some kind of average over all the possible initial conditions. So this is what I want to do. Find the B or the C that minimizes the trace of LK. Similarly, in the estimation setting, we know that the Kalman filter has this expression, so it's linear. Here we see the output coming in, and we have this matrix K here, which is the solution to this Riccati equation, very similar to the other one. A becomes A transpose, C becomes B transpose. But in addition, we have that the error covariance is also equal to K. So if I want to minimize the expected estimation error, I'll have to minimize the trace of K. So we again have a very similar problem, minimize trace of LK, where K obeys the Riccati equation. Okay? And we want to do this over this parameter here, C or B. Okay? So that's a problem statement. Now, there is an obvious trivial solution, which is, well, if you want to have a good estimation, improve the quality of the sensor. Just buy better sensor or buy better actuators. Then you'll do a better job. So what does this mean here? If I let the norm of C, all things equal, I increase the norm of C, you see that C multiplies X. So in the signal Y, the signal to noise ratio will improve, and my estimation error will decrease. Something similar here happens when you look at actuation. So can we actually formalize this? And the answer is yes. This was done actually about 20 years ago, even more, 25 years ago. And these were the first results that I've seen along this area, this type of studies of the Riccati equation. So here's what these results says. And the first trace I could find of this is this paper by Giromel from 1989. And the result has been rediscovered many, many times. Okay, I think it's still being rediscovered today. So if we look at this Riccati equation, now think of R here as a parameter. You want to study the behavior of K as a function of R. So what Giromel proved is that K was monotonic decreasing with respect to R. In fact, it was a concave function, with respect to the variable R. Now let's go back to our setting where here I would have B transpose. If you think of these here vector, a column vector, a row vector, R has to be a scalar. As R increases, the signal to noise ratio, you can think of it increasing, and K will decrease. This is what this says. So this kind of generalizes this intuitive idea that as the signal to noise ratio improves, the estimation error will decrease. So now what we want to do, of course, is we have a limited budget, like in all universities. So we're going to keep our budget, we're going to keep our SNR, and we're going to try to find the optimal sensors for a given SNR. Okay? And this is what is going to make the problem, or what made the problem much more difficult, and why there is so much literature on this problem. You're going to see it's going to become a non-convex problem. Okay? So here I also mentioned that there is a lot of other work, mostly in the infinite dimensional case by these various people, and also in application-driven settings. So if you Google optimal sensor actuator placement for, you'll find plenty of applications for this type of problems. Okay, so what are we going to do? We're going to normalize C, as I said, and we're going to use this notation here. Gamma will be the SNR, if you wish, and I'm going to let the norm of C to be equal to P, where remember that C here belongs to RPN. So P is the number of observing signals I have. I normalize it to P, just a convention. If P is greater than 1, I'm going to require that this outer product here, this inner product of C and C transpose, is a P by P identity matrix. So if I have 3 sensors, they give me 3 rows which are orthonormal. I have a frame for the sensors. So that's a restriction I'm going to put. We say that C belongs to the Stiefel manifold. Now the same problem as before is to find the minimum of LK, where K obeys this equation. Now I see the parameter gamma popping out here, and I have C transpose C here, where these are normalized. L and Q positive definite, they're just user-chosen parameters. And I'm going to use C bar only in this slide. Now I'm going to use C, and this is going to be the equivalent of C bar later on. So C is going to be normalized, and we're going to see the gamma in every equation. Okay. Okay, so now I can start stating the results. So first, a little bit of terminology. I'm going to let capital C be the outer product of C and C transpose. I'm going to use this notation. And this function trace LK, I'm going to call it J of gamma C. So it depends on this parameter gamma and on C. It depends on little c through big C. Okay. So that's a function. I call a point here C critical if it's a critical point of J, and it's optimal if it's a global minimizer of J. So we will be interested in the global minimum of this function J. And finally, last bit of terminology, for an arbitrary positive definite matrix M, I'm going to call the p-dimensional invariant, I'm going to call the highest p-dimensional invariant subspace of M the invariant subspace associated with the p largest eigenvalues of M. So fairly natural terminology, okay? Okay, so here are our results. So an observation matrix C is going to be a critical point of the function J if the span of C, so we're going to see the only thing that matters is not C, but just a vector space it spans. If the span of C is an eigenspace of this matrix, which is a positive definite matrix, defined as a product K RK, where K is a solution of the Riccati equation, and R is a solution of this associated Lyapunov equation. All of these will have positive definite solutions, so M will be positive definite. So C is critical if it's an eigenspace of this matrix. Now this matrix depends on C. So this I just characterize with the optimal R. If you give me an optimal, I can check whether it is one. I can't really use this equation to find the optimal observer yet. Okay. So the next result will be that for L and, well, generically for L and Q, these were the parameters I had, symmetric positive definite, and for P equal to 1, we will have a unique optimum, actually. So there is unique optimal observer. The problem is not convex, but we nevertheless have only one optimal observation matrix. Of course, up to a sign, because C enters as a product C transpose, so the sign is irrelevant. Okay. Okay, so here, this was a restriction I mentioned earlier. If P is larger than 1, we impose this restriction. So same assumptions as before. If P is larger than 1, then we again have a unique optimal orthonormal observation matrix, big C now. And it's such that it is actually a projection onto the pth highest invariant subspace of M. Basically, what I'm saying is that this matrix C here, which is made of orthonormal vectors, will be the highest invariant subspace, or the p highest invariant subspace of M, aligned with the highest eigenvectors of this matrix M. Okay, so at this point, we still don't know how to compute them. These are just characterizations. So a last characterization here that we obtained of the problem, so this is perhaps for the specialists. So what we're going to do essentially is show that the function J is a Morse function. And we're going to see in a few slides that it's a Morse function on a Grassmanian. I've hinted several times that the only thing that mattered was the span, not the matrix itself. So truly, we have an optimization problem on a Grassmanian. So you can ask whether the function we get is a perfect Morse function. And the answer is no, it's not a perfect Morse function. We get many more critical points than the one Morse theory would require. But when I made a comparison with the number of critical points I obtained of every signature and the Poincaré polynomial of the complex Grassmanian, I get a perfect match. So somehow this problem is very canonical because we recover here the Poincaré polynomial of the complex Grassmanian. So this aside being said, now here is an algorithm. If you want to find the optimal observer, what you have to do is just go onto MATLAB and solve this equation. You start here with a C, which is orthogonal, a projection matrix of rank P. Solve this differential equation, let it flow. So it's the gradient flow of my cost function, and it will converge with probability 1 to the optimal observer or to the optimal actuator. Okay. So this is the algorithm that tells you how to find the optimal observer for the Kalman filter. Okay. Are there any questions up to this point? No? Okay. Yes, Alan?
is that double bracket equation the same as sort of finding the largest eigenvalues?
Yes, so
numerical approach to sorting eigenvalues?
So the base idea is the same because we're going to get a flow on the space of symmetric matrices. But here I'm not trying to optimize. I'm optimizing a very different function. So the double bracket appears because, you're going to see in the next slide, I recast the problem as trying to optimize on an adjoint orbit. Okay. Okay, so here is a brief summary of the approach. So what I'm going to do in the next slide is represent the state space, as one says, a geometric object. So even though I said this a few times, we're going to see that truly it's an optimization on the Grassmanian, on the set of subspaces. I'm going to compute the gradient of the cost function. So that will be easy enough. Find its critical point, and then evaluate their signature. So let me here briefly remind you of what the signature of a critical point is. So here we have a function which is function from R2 to R. The signature of a critical point is a zero of the gradient. The signature is a number of positive eigenvalue of H. Then you put next to it the number of negative eigenvalue of the Hessian, sorry, H is a Hessian, and then the number of zero eigenvalues. If you have no zero eigenvalues at a critical point, you say that the critical point is not degenerate. Okay. So here, for example, a minimum has a signature of 2, 0, 0, two positive eigenvalues for the Hessian. Think of x squared plus y squared at 0, two positive eigenvalues. A saddle will have a mixed signature. A maximum will have all eigenvalues negative. Okay? So these are the signature of the critical points. For this example. Okay, so in the case of p equal 1, if you remember the form of J, which is trace of k, where C enters k through C transpose, it's clear that J of gamma C is J of gamma minus C. And I said I'm going to normalize C. So C lives on the sphere, and I identify antipodal points. So I have a projective space. And so this is just a space of directions in Rn. And we know that this space is also the space of orthogonal projectors into one-dimensional subspace, or n-1. Meaning if you give me one projection, one direction, I can also say, okay, I'm going to look at the projector along this direction. Okay? So this will be the space of matrices C, such that C squared is equal to C, a projection matrix, and the rank of C equal to 1, projecting on a one-dimensional subspace. Okay. In the case of vector, sorry, that should not be here. In the case of vector-valued observation, what we had, and if I had the Riccati equation, I do not have it nearby, it would be clearer to see that J of gamma C is J of gamma theta C. For theta, an arbitrary rotation matrix. So what does this say is that if you give me n vectors, or p vectors, and they span a subspace, if you rotate these vectors, the cost function does not change. So the exact vectors do not matter, only their span. Okay. So here again, we have an optimization problem on the Grassmanian GRPn. Okay. So Grassmanian, I thought I would put a picture here of Grassmann because whenever I feel like complaining about my teaching assignments, I remember that this guy taught high school math for a living and Latin and other subjects because he could not get a faculty position. And yet he did work that is still remembered today. So, and he looks very much like a high school math teacher, I would say. Okay. So the next step is, okay, we have figured out that we have, if you want to solve the optimal sensor placement problem, we have to solve an optimization problem on a Grassmanian. So computationally, the only thing we have to do is compute the gradient. So how are we going to represent this space? As I said, we can represent it as a set of projectors. So for the p-dimensional Grassmanian, the set of matrices which are symmetric positive definite, such that C squared is equal to C, I have an orthogonal projector, and the rank is P, meaning I have a projection of p-dimensional subspace. And how can we represent this space? Well, as a space of matrices theta, lambda, theta transpose, where theta is orthogonal, meaning theta, theta transpose is equal to the identity. And lambda will have p entries equal to 1 and n minus p entries equal to 0. And if you choose lambda like this, you can easily check that, sorry, there is a parenthesis here missing, theta transpose lambda theta squared is equal to theta transpose lambda theta, and you clearly have that the rank of such a matrix is equal to P. Okay? So this is a nice representation of the space of rank P projectors. I'm going to call also the space proj and P for the space of projectors in n-dimensional space onto p-dimensional subspaces. Okay. So let me actually go to the next slide first. So we need to do an optimization on this space. So here is a brief slide telling you how to do that. So you know that when you want to optimize a function, usually you look at its gradient. If I have the function j, we can think of the gradient as dj over dx. So that's not going to work when we want to optimize over a manifold. So we can also think as the gradient as giving us first order variation of j in any direction. In this sense, if I want to compute the first order variation in j in the direction v, is the product of the gradient with v. Okay, so once we have this form, we could imagine having here in between a positive definite matrix that will define a certain metric. And so I could think of defining the gradient in this way. The gradient will be the function here, grad j, such that for any v, this equality holds. That comes very naturally from the original definition of the gradient. And this is a definition we're going to use when we want to find a gradient on a manifold. Now, the only twist is that we cannot go in every direction v in our n, but we'll need to restrict at every point the number of directions we can go to. That will be the tangent space. So here is an example. If I want to look at the tangent space of the sphere here at this top point, I cannot go in all directions. I have to make sure that I don't go up and down. So it's a set of vectors which have this form. Third coordinate is 0. So the part I skipped from the previous slide is the following. Compute here, and it's a fairly standard computation, the tangent space of the space of projectors. So these are the allowable variation to my function. Okay? So if I take variations like this, then I'm sure that I will stay in the manifold of projectors. Okay, the other part is choosing a metric, the matrix G in the previous slide. And so here the one we're going to use is the normal metric. And the normal metric actually seems to have a complicated definition, but it's a very natural metric in the following sense. So there is a fundamental object, a fundamental metric, which is called the killing form. And I'm going to show you in the next slide how fundamental this metric is. And it's just the trace. So the inner product here of omega 1 and omega 2 is minus the trace of omega 1, omega 2. That's called the killing form. Okay. Now we've seen that the tangent vectors for my manifold were of this form, add sub c omega. And this is a shorthand notation for c bracket omega. Okay, so perhaps what we want to do is undo the at c and use a killing form. Problem is, at c is not invertible. So what we do is that we make it invertible in the most trivial way. We restrict its codomain to its image, and we mod out by its kernel. So this is what folks that started with the introducing the normal metric did, and then you get this form for the normal metric, which looks a bit complex, but it's really quite natural. You just undo in one well-chosen way the action here of this at c, and then you use this very natural metric, which is the killing form. Okay. So this is when it was introduced, and as was already mentioned by Alan, Brockett in 89, 92 looked at problems defined on such manifolds where he also used this normal metric. Okay. Okay, so why is the killing form so important? It's because this was, according to Mr. Kalman, the greatest mathematical work of all time. So if you Google greatest mathematical paper of all time, and you'll find an article in the Mathematical Intelligencer that makes a case here for the work of Wilhelm Killing on the killing form. So it spurred a lot of work. It's an interesting read, and especially this section on why was this work neglected. So this paper appeared 100 years after the work of Killing. So certainly it's not Killing that affected personally Kalman to write such a paper. Okay, so this was for the terminology. So now we can go on and do the computation. And so I'm going to spare you the computation, but I can tell you that you can compute then the gradient of the function j on the Grassmanian, the way we have represented it. And the gradient of j is this matrix, is this vector field, C bracket M, with M defined as I have defined it before. Okay, so this will give us the gradient flow. And the other here conclusion is that an orthonormal observation matrix is critical if the span of C is an eigenspace of M. So that's something I told you at the very beginning, and that's now an easy consequence of this general form of the gradient flow. Why is that? Well, in order to be a critical point, we need C, this product here, to be 0. This is 0 if and only if C and M commute. These two matrices need to commute. Both matrices are symmetric positive definite because of some reason related to the solutions of the algebraic Riccati equation and the Lyapunov equation. And two such matrices will commute if and only if they share eigenspaces. And so we have automatically the first statement, as I've written here. Okay, so now is the result that's going to tell us that we have, we're going to converge with probability 1. So there are some assumptions on the system. I'm going to require that the system be stable and that gamma, the signal to noise ratio, is not too big. So gamma small. Generically, for L and Q positive definite, when I restrict myself to the case of scalar observation, so P equal to 1, we can compute all the critical points of J. It will have n, where n is the dimension of the system, and here are the respective signatures. So this is a minimum, this is a saddle point, where you decrease in n-1 direction, n-2 direction, go up in 1 direction, all the way down to the maximum. And we can also characterize each of these critical points and give them some meaning with respect to the corresponding invariant subspace of M. So what does this result say? It says that J, which is a function that's not convex, nevertheless has only one minimum. And so if we use a gradient flow, we're just going to end up at that minimum. Okay? So in order to do this, we had to look at all the possible critical points and evaluate their signature. Okay, the case of the vector observations is a bit trickier to handle, mostly because there is some combinatorics showing up. So I'll need to give you a little bit more terminology. If D is a positive integer, we call a partition of D with P parts P numbers, positive integers, whose sum is M. So this is a partition whose sum is D, sorry, this was a bit confused. This should be D. So P integers whose sum to D is a partition of D in P parts. It is a distinct partition if none of these integers are repeated. That's a distinct partition. Okay, so we need to add a twist to this. We need to look at partitions where there is a maximal value. So I call P sub n of PD. This is a number of distinct partitions of D into P parts. So I have M1 through MP, none of these repeated, they sum to D, and I'm going to require that all the MIs be smaller than N. Okay? So that would be a restricted partition. So here is an example. So this is P6 to 8, so partitions of 8 into 2 parts with no parts larger than 6. There are only 2, 8 as 6 plus 2 or 5 plus 3. You cannot use 7 plus 1 because then 7 is larger than 6, and you cannot use 4 plus 4 because that repeats a number. Okay? So you only have 2, and here they are. These are related to what's called Gauss's Q binomial coefficients. Okay, so why do we need this? Because this shows up when we try to count the number of critical points or analyze the critical points of our cost function in the vector observation case. So if you allow yourself to have p observation signals, how many critical points to the optimal observation function will you have? You will have a lot, and choose p of them. If you give me a signature like this, n plus s minus, you ask me how many of these critical points will have n plus positive eigenvalues, n minus negative eigenvalues for the Hessian at that point. Well, here is the answer. So it involves this kind of these combinatorial type of statements. So this would be the number of critical points with index n plus, n minus, and 0. In particular, all the critical points are non-degenerate. None of the critical points have 0. This means that this is indeed a Morse function. And perhaps more importantly, in terms of applications, there exists only one minimum and only one maximum that we don't care as much unless you want to maximize the observation error, which I think few people want to do. But also we only have one critical point which has an attractive subspace of dimension d minus 1. So if we had more of these, convergence could be a bit slow or even derailed, but we only have one. So all the other attractive or stable submanifolds for the gradient flow will be of codimension 2 at least. Okay? So the algorithm in practice converges quite quickly and quite well. Okay, so actually I went quite quickly, so I'll have the time to discuss the proof from 20,000 feet view, really. So how do we prove such results? First of all, we look at the limit where gamma is equal to 0. And we check, so extremely low SNR, actually no observations at all. And you check that you have a finite number of critical points. Okay. Now, what we can do is try to verify that these critical points subsist when gamma increases. With the gradient flow that we have, that's something that's quite difficult to do. So what we do is that we introduce another vector field, but we can show that this other vector field f has the same 0 as the gradient. But this vector field we can actually analyze. And we can verify that as gamma increases, the zeros of this vector field basically don't move too much. And in particular, the number does not change. So we introduce this auxiliary vector field, do some analysis, and show that it behaves well. Hence, the zeros of the gradient will behave well as well. And finally, we can evaluate the Hessian at all these critical points. For those of you who have done this type of computation, usually the Hessian is quite messy. Here it's extremely messy, but you can do some approximations of the Hessian for gamma small. And this is mostly why I have this assumption that gamma cannot be too big. Otherwise, some terms in the Hessian become dominant and they're too difficult to analyze, at least as far as I can tell. Okay, so a bit of an outlook. So I guess the summary is, if you want to find the optimal sensor for a Kalman filter, well, we can do it. You just have to solve the gradient flow that I presented. The problem is not convex, but it's nevertheless well behaved. Same problem applies to finding the optimal actuator in an LQ control setting. You might wonder about the infinite dimensional case, because these type of double bracket equations have been extended to an infinite dimensional setting. So here we don't know if the same problem could be, or the same proof technique would apply. So here is something else which I find, well, we know how to prove, but I still find puzzling. I put the restrictions that when I had, let's say, 2 sensors, they had to be orthogonal. Now imagine that I also let them move. So I lift this restriction. And I say, well, so the sensors can move, but they still have a limited budget. So I cannot increase their norm. And I let gamma be small, and I try to optimize over the sensor placement. What's going to happen as gamma gets small? Are they going to get far apart so that we can spread, if you wish, our observation as much as we can, or are they going to coincide? Anybody wants to venture a guess? So they will always coincide. And this is something we don't, I mean, there are parallels in our communication as to when you have very little energy, you're trying to send a signal, is it better to spread it over 2 antennae or to use just 1 antenna? It's better to use 1 antenna. Here we also see that as gamma gets small, if you have a lot of freedom, it's better not to use it. Put everything in the same sensor. And as your budget increases, at some point, you'll see a bifurcation. When the signal-to-noise ratio gets better, suddenly it's okay to buy another sensor. Analyzing at which level is it okay to buy this new sensor is something we do not know how to do yet. Other case that we can look at is a case of A unstable. So that's perhaps easier to understand in the case of controllability, control. If A is unstable and I want to choose the optimal B, the first thing I'll have to do is make sure that I compensate for the unstable modes. So that makes the problem a bit more difficult, mostly because the Riccati equation that we have is not as well behaved. Okay? And finally, you can also think of a joint controller and observer design problem where you do an LQG. So you feed the output of a Kalman filter to an LQ controller and try to optimize over both C and B. And the problems here are still open as well. And Dr. Xudong Chen is working also very much on this problem. And I think I will stop here right on time. Thank you for your attention.